Okay, so we have talked about in our last section 11.5 lines in space and then planes in space. And now we're going to talk about surfaces in space, so making things a little more arbitrary. We're going to have quite a few different images showing up, which is why this is inside of the pictures and so forth. They're going to be in here today. These are all in your book. They're all in WebAssign, so you can go and access these pictures later. So if you want to sketch yourself a real quick sketch of something, that's fine, but don't try and be meticulous on drawing these in. That's not going to make a lot of sense later. You might just reference yourself that you can go back and look at those. So to start with, what's that?
It's not art with Dr. Dar or Dr. Drake.
No, it's going to be a lot of good art, though. You're going to see some fun images today. So the first one we're going to talk about is fairly boring compared to some of the other ones. It's cylindrical surfaces. So we're going to consider our standard cylinder from geometry, where your base is a circle of radius 5. In 3 dimensions, this would look like the equation x squared plus y squared equals 25. It would be a right circular cylinder. So imagine a paper towel roll, but it's infinite in terms of its height and length, right? It's infinitely long. Or a pole. You can think of it as being a pole. Okay, so now we're going to consider the intersection of that surface, right, this sort of infinite heighted cylinder, with the plane z equals k for some constant k. Since the equation has no z's in it, the intersection with every such plane, which is what we call the trace of the surface in the plane z equal k, is the same. It's a circle of radius 5 centered at the origin. You can also think of it as taking that cylinder, that paper towel roll, and you're just cutting it in necessarily half, but into a piece that's straight across, like 90 degrees, perpendicular to the surface itself, and you would be creating cross sections that are circles. So now we're going to generalize some of our vocabulary. More generally, the cylinder is used to refer to any surface whose traces in every plane parallel to the given plane are the same. Equations of cylinders will have only two variables. So very specifically, we talked about it being a right circular cylinder. Right, it's a circle in every plane that's parallel to the z-axis, or the z-plane, or the xy plane, the z-axis. But what happens is we could do things like an ellipse, and it would also be considered a cylinder, right? Make it an elliptical. So, this is the paper towel roll or the toilet paper roll that gets squished and it's sort of elongated, right? We would still call that a cylinder. So the equations will all look like, or at least similar to that x squared, this one, which was x squared plus y squared equals, say, 25. But more specifically, there won't be a third variable. A lot of the other equations we have are going to have a third variable, of course. And you're going to end up getting squared terms, right? So it's x squared and y squared, or it could have been x squared and z squared. But they don't necessarily have to have the same coefficient in front of them or anything like that for it to be considered a cylinder. So the components that it does have to have are two variables that are each being squared, right? And the third variable is not present. All right. We're going to look now in general at what happens when we have any or all of the variables, and what that's actually going to be called is a quadric surface. So a quadric surface is a graph of the form ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus gx plus hy plus jz plus k equals 0. The actual equations we do are going to look much cleaner than this crazy one right here, okay? And what happens is that in addition to the cylindrical surfaces we just talked about, we create 6 additional surfaces using this form, or this equation, general form of the equation. And those 6 different surfaces are an ellipsoid, a hyperboloid of 1 sheet, a hyperboloid of 2 sheets, an elliptic cone, an elliptic paraboloid, and a hyperbolic paraboloid. So where we're headed next is through each one of these 6 different descriptions, or verbal descriptions. We're going to have a picture that's associated with them and the form of the equation that's associated. The important piece for you in terms of being able to replicate something is recognizing how the forms of the equations you're given either already look like or can be changed to look like one of these 6 specific, well, 7 if you consider the one we already did, forms, and identify which one it is. Okay? That's what we're going to be doing. Hannah? There will be. Yeah, you'll have a note card on your test. Yeah. Okay. That's a fair question. There's a lot of memorization in this particular chapter, a lot. Okay, you ready to take a look at some fun pictures? And these are really fun pictures. You're just going to be glad you're not having to draw them because they're not necessarily easy to draw. So here's our first one. So this is an ellipsoid. So the image you should have in your mind is, like a sphere, but it's an ellipse that's been made into 3 dimensions instead of a circle made into 3 dimensions, right? That's an ellipsoid. The formula looks much like the ellipse formulas we were seeing back in chapter 10, right? It's just got the 3rd dimension, z squared over c squared. Other than that, it's the same formula as we saw for an ellipse. You've got things that are being squared, right? You've got the whole equation equal to 1 with different denominators, of different values. The the dominant or like which direction it is sort of more long, elongated than others has to do with which of those A, B, and C values are larger. If you do have the case where A and B and C are equal to each other and they're not zero, that's the case for a sphere, right? So imagine that you had x squared over 5 plus y squared over 5 plus z squared over 5, right? They're all over the same value. That's the same thing as x squared plus y squared plus z squared equals 5, and that's the equation of a sphere. Okay, so this is just a general idea of way spheres work in a specific case. Okay, good. Ready for the next one? This is a hyperboloid of one sheet. Now take a look. It does look a little like a cylinder, right? It didn't change.
Hyperbola around an X or Y axis.
Yeah, it is kind of like turning a hyperbola around an axis. You can also imagine that you can describe why this isn't a cylinder very quickly. Although the cross sections are parallel, if you were to cut through them and so forth, they wouldn't all be the same, right? The width is varying at different points in the hyperboloid of one sheet. It is valuable to notice that the axis, right, that's going straight up and down here is the z-axis. Whichever one of the three variables is the negative one is going to have, that's going to be the axis around which the hyperboloid of one sheet is sort of centered. So we can take the same equation, and the point being that everything's being squared, x squared, y squared, and z squared, but one of the three is negative and the other two are positive. So we're going to change these up as we continue going on which things are negative, which things are squared, different stuff like that. This one has the feature that we have all of them being squared, and one of them is negative. And the one that is negative is the axis around which we're centered. Okay, you ready for the next one? Okay, so the next one is a hyperboloid of two sheets. So can you picture this particular equation? And it's sort of like it's separating. You've seen those like, jars that have the like blobs inside of them and the blobs separate. That's the picture I have in mind here. I've got something that is separated and part of it comes up and part of it goes down, and now there's this gap in between it. So this is a hyperboloid of two sheets, and of course you can see why it's two sheets is there's two different pieces to it. What's different about the equation? There's two of them that are negative this time, right? And this time, the axis around which it's centered corresponds to the positive piece. So it's not drawn in here, but we could certainly do it. This is what I mean by the axis, right? And this would be the x-axis on this one, because the x value is positive for this graph. And remember, all of these are set equal to 1, so that's the part we're holding sort of fixed as we're making our decision about what's positive and negative. We have 1 on the right-hand side. Okay, ready for another one? Okay. This one is an elliptic cone. What's different? Oh, man, what is going on with my projector today? Okay, we're back online. Elliptic cone. All right, so, I think that Annika said it. What's different about this equation?
0.
It's equal to 0. At first glance, it looks a lot like the other equation we had seen, right? The one for the hyperboloid of one sheet. I do have x squared, I have y squared, and I have a negative z squared, so one of them is negative, but this is actually equal to 0. And instead of having a cone, the way we think about our cones typically, this one would be elliptic, right? It could be circular, but it could be an ellipse on the top, the circle part of it, the shape part of it. And it's actually opening in both directions. It opens upward and downward in the way that this is being drawn. It's also going along with the negative axis, just like the other one was on the hyperboloid of one sheet. So whatever the axis is, it's negative. This one was z. Z is going to be the axis around which it's centered.
Are these things like the base equations that any of the one variable could be negative, or is it always gonna be z that's negative?
It could be the A is negative or the B that's negative. Yeah, any of the pieces can be negative, but only one of them. And it would just change the direction. So if you can imagine sort of swiveling this so that it opened sort of coming out of the screen at you along the y-axis or along the x-axis, you can definitely have that happen if that were that negative value instead of the Z or C, depending on how you think of it being negative. Okay, 2 more. Elliptic paraboloid. It's like a bowl shape, right? Yeah, and the cross sections are ellipses, yes? This equation is quite different. What's the biggest difference maybe that you notice?
X and y squared equals z.
Yeah, it's z and not z squared though, right? That's a big difference, right? All the other ones so far have had all of our variables squared. This one does not. And while you could put the z on the same side with the x squared and the y squared, that'd be fine. It still wouldn't be squared. So whichever variable is not squared, that's the axis we're centered around. So the linear variable is the axis we're centered around. Okay, one more picture. This is the best one. I'm going to do my best to attempt to draw some of these later on. You'll see how bad it goes, but nonetheless. This is a hyperbolic paraboloid.
Well then.
Well then, the image you should have in mind is a saddle for a horse. Yeah. Of course, it's infinite dimensional, right? Like not dimensional, but infinite in size. It continues on up and left and right and down and all that forever. But this portion of it looks a lot like a saddle for a horse.
Are we going to have to draw anything like that?
You'll have to sketch some things potentially, but I'm not going to hold you accountable for being precise. How's that? Okay. The axis, again, corresponds to the linear variable. How does this equation differ from our elliptic paraboloid on the previous screen?
It's subtraction instead of addition.
Yeah, I still have one of the variables that's not squared, but I have subtraction between my two squared variables instead of addition between them. And then we end up with a hyperbola that's happening for us. So it's a hyperbolic paraboloid. Okay, so you ready to see how this works with your questions? All right, so we have questions like this. Describe and sketch a surface. This is how all the questions are going to be pretty much phrased. Describe and sketch a surface. So taking a look at this particular equation, we have something which I think I maybe misspoke when I said it earlier, now that I'm thinking back to what I said. But this says y equals x squared. So what you're going to do is you're supposed to be looking back at the 7 different forms that we had, 6 of them that we kind of all grouped together, and then the first one that was sort of separated off a little bit, and decide which of the 7 that we had does this one fit the equation for. Which one? Oh, Jubal says none of them. It does. It fits the equation for one of them, but I think I misspoke, which is probably making things sound funny. It's not a paraboloid. The first one that we did, I'll flip back over there. The cylindrical surfaces. This was an example of one. There was one example, x squared plus y squared equals 25.
So would it be a hyperbolic paraboloid?
Nope. How many variables are in this equation? 2. There's only one equation that has 2 variables. There's only one. Which one was it? The first one, the cylindrical one, right? And I totally misspoke when I told you earlier. I said something about them both needing to be squared. They don't both need to be squared. Even as I said it, I was like, I don't think that's right, but I couldn't remember for sure. They don't both need to be squared. But as you take a look at this, this will be a cylinder. And as we're drawing it, let me get my lines to be lighter color. The graph will look like a parabola if we were to only consider y equal x squared. You know what the graph of y equal x squared looks like in 2 dimensions. What's it look like? Yeah, like this, right? I mean, it's your basic parabola like this, yeah? So it's going to look like that, but then 3-dimensionalized. So if you can imagine, here's your y, and here's your x, and the y-axis is the one that's supposed to be extending around. So I'm not going to be able to draw well because I don't do this very well, but it looks something like that, right? Except opening in the positive direction because it's still not right. How about this one? That's the one I want. Okay, so this is my x-axis. It's opening upward on the y-axis, so towards the positive y-axis. But then I need to 3-dimensionalize this. How would I do that? That's what I hate about being wired in. I can't pick the thing up. Okay, so what we're going to do is we're going to draw that same image up here. Okay, and then we're connecting it, whoops, like so. Can you imagine taking a piece of cardboard and sort of curving it? That's the image that I feel like this looks like, is a piece of cardboard curved. Okay, so when you're drawing it, we're not focusing on, we're identifying the name, right? I wrote cylinder. We're not focusing on like precision in terms of like plotting points. That's not what we're doing here. This is really a sketch. It's just a sketch. In terms of the cylinder, if you wanted to be more specific, could we write something that would be a little bit more specific than just cylinder? What kind of a cylinder is it? It's a parabola, right? So making it an adjective, it's a parabolic cylinder. It is a right parabolic cylinder because we do have it perpendicular to the XY plane. So if you wanted to write that word in there, that would be okay. But generally speaking, this is a cylindrical surface. It's the first description we saw. Ready to try another one? 9x squared plus y squared plus 9z squared equals 9. So, ellipsoid. And what makes it an ellipsoid? Like what clues you in that that's it?
All 3 terms, they're all addition, they did all equal 1.
Okay, and they're all squared too, right?
Yeah.
Yeah. Now, it's not in the standard form that the ellipsoid equation's in. What could I do to change it, though? Yeah, I could divide everything by 9. So if I divide each of the pieces by 9, we end up getting x squared over, say, 1, right? I have y squared over 9, and I have z squared over 1, and this is equal to 1. So this is the standard form that we would want to put this in. And you would change it to standard form. That's something we're going to do. Jubal's exactly right. This is an ellipsoid. And as we do the sketch, we have our value looking, it's still centered at 0, 0, 0, right there in the middle. Which is the one that's going to be dominant? Which axes? Can you tell? Like which one's going to be longer? Y, because the value underneath y that's being squared is a 3. So it's sort of elongated along the y-axis. So if we were able to draw this well, which I'm making no promises, it would look something like this. Yeah? And then we got to make it look like an egg. It's terrible. Absolutely terrible. Let's try again. I don't know if that got any better. It's a football. How about that? It's more or less like a football shape. Okay, but can you tell that it's definitely not a cylinder? Okay, we're good. It's definitely not a cylinder. Lovely. All right, the next couple are a little easier to draw. You ready? Another one? I think this one's hard. I think it's hard to three-dimensionalize a circular shape like that. All right, how about this one? X squared plus y squared over 4 minus z squared equals 1. It's which one?
Hyperboloid one sheet.
Ah, it's a hyperboloid. Boloid, there we go. Of one sheet. So the hyperboloid of one sheet looks kind of like our cylinders, right? Except that it's kind of an ellipse on the top and an ellipse on the bottom, or a hyperbola on the sides, however you want to think about it that way. Which axis am I centered around? Z. Now, let's just say for a moment it had been Y, and you're like, man, it would have been nicer for it to have been Z. You can draw it the way you want to draw it and just label the axis that normally we would have labeled Z as Y. You can do that, so just, don't go over thinking like, how do I make that along the right axis? Just make it along the axis you want to label it along and then draw it that way. So this is our Z axis right here. And so we have something that looks like this. Is that all right? Told you that one's easier to draw, right? Definitely. The hardest one's coming though, but not in the next one. All right, how about this one?
Elliptic.
Yeah.
Paraboloid.
Elliptic paraboloid. So what about this makes it an elliptic paraboloid? Like, what are you identifying as being some of the key ideas? Y is linear. And we're adding. Those are the key ideas, exactly. So we have elliptic paraboloid. So an elliptic paraboloid looks like what? A bowl or a cup, right? It looks like it's going to hold something. And which axes do I want to label my vertical axis this time? Y, you bet. So this one's going to be Y up here. Whoops. I'm still not hitting the right button. There we go. And our graph is going to look like a bowl of some sort. I'm setting the expectation very low for your pictures, right? Yes, that's the goal. But you can see it there, yeah? You can.
Looks like I only have to take like cross sections
This
of.
is exactly cross section.
Exactly.
Yeah.
Yep. All right, let's take a look at number 5. And the form in which it's given is a little funny. So now what?
Elliptic cone.
Okay, so how did you decide, Jubal?
Square both sides, and then we subtract z squared.
Okay, does that look right? Did you all the shifting around of things okay? Yeah, this is what it looks like. It's a little bit funny that I have the 4 next to the y squared. We could divide by the 4 on all the pieces as well, if you wish, and then it actually puts it into the form that looks a little bit closer to what we have, or more like identical to what we have, really. So I have x squared over 4 plus y squared over 1 minus z squared over 4. Okay, so it's an elliptic cone. There is one caveat to being elliptic cone as we draw it. Any idea what that might be? Let me ask a different question first. Which axes do we want to be our vertical axis? Z, I agree. So we want our z axis to be our vertical axis. If I were drawing an elliptic cone normally, it would look like this. That's terrible, but something like that. I contend that I only get the top half. Why might I only have the top half?
Because it's positive square root.
Yeah, when a square root is already located inside of a problem, it's the principal square root, which means that the z values should only be the positive z values. And if z is my axis up here, I can only have positive z values, which means above the xy plane. That's a terrible z. That's better. Does that make sense? So I've made it look more, maybe less elliptical than it really should, but you can imagine sort of collapsing it or elongating it. And I didn't write it, but we will. So what did we say this was? A elliptic cone. Okay. About 6.
Hyperbolic paraboloid.
Mm-hmm. It's the hardest one, I think, to draw. Maybe the ellipsoid is pretty close, though. This is a hyperbolic paraboloid. Let me actually move it down just a little bit. Let's put it into standard form while we're at it. Is there anything we need to shift? What would we need to do? Oh, I've got that written differently. What might I need to do? Yeah, just dividing by the 4, right? So if I divide by the 4, I have x squared over 4 minus y squared over 1 plus z over 4 equals 0. I think, look back at it the way this book does it. I think it's not quite in the form that they have it, though. They have the form, I'll write it up here as, like the version, as our standard version is z equals x squared over a squared minus y squared over b squared. So if I were trying to get it into that form, what do I still need to do? There's something funny. Let me actually undo what I just did with the division by 4, and we'll shift first.
Subtract z over 4, and then divide by -1.
Yeah, let me move the z first. So actually, I think I'll leave the z where it is because it's already positive. I would be actually having a 4y squared minus x squared if I do that, right? I want the z to stay with a coefficient of 1 and not have a denominator. So I don't really want to do the division by 4 that I tried to do just a moment ago. How can I still do it so that it represents y squared with a denominator? Any ideas? Not quite. I want the coefficient in front of y squared to be 1, but there needs to be a value underneath y squared as well. There's a 1/4, yeah. So instead of multiplying by 4, we can represent this as dividing by 1/4. And we sort of do it in reverse all the time, but it's equally true that I can write it that way. That would be the standard form that we would be looking for. It is a hyperbolic paraboloid. And as we draw it, it's actually in the form, because it's the z value itself, of the one we saw before. So let's reference back. I'm going to show you back the picture where we were, because it's the hard one to draw, I think. So it looks like this, and we're going to attempt to draw that picture on the previous slide. Well, on our further slide. And I don't have it written in very well on mine. So it looks something like this. And it looks kind of like that. Nope, that's not right. Like that, right? No, I think I kind of want that there too. You can kind of imagine shading over here like this. And then there's shading around. I don't think that's very good either. That might be better. That's not better. I think I want that there. Yeah, that'll work. You can imagine it goes up and over, right? Each of these traces go up and over to the other side, just like like stitching along a saddle would go across there. It's fantastic. That's beautiful, Annika. I should take a picture of it, and I should use your picture instead of mine. Look at that. That is fantastic. Art at its finest. All right, we have one left. There's only one we haven't drawn. Have you been keeping track?
Yep.
Which one is it, Jubal?
Hyperboloid of 2 sheets.
It is. Is this the correct equation for a hyperboloid of 2 sheets based on the details we looked at?
Yes.
Yeah, it is. Let's get it in the right form, though. It does not look like it right now. The form that we're supposed to be putting it in, hyperboloid of 2 sheets, that was it. Looks like that. So I have the first one, the positive term, and then I've got my 2 negative terms. They're set equal to 1. So all those details are what I'm going to try to get mine to look like. All right, so what kind of shifting might we want to do? Somebody tell me something. Divide by 9, okay. So you can divide everything by 9. That's a good one. So now I have negative x squared over 9 minus y squared over 9 plus z squared over 1 equals 1. The only other thing that we could do that makes it look a little bit more like what we've seen before is if we move the z squared in front. You don't have to necessarily move it in front, but then it matches up like perfectly in terms of the signage of the other one. All right, so take a look over here at the description. One more time. That's it. The axis corresponds to the variable with positive coefficient. So this graph, I labeled it as x because the x had the positive coefficient. What is it in ours? It is z. So as I'm drawing this, I will actually let the z be that vertical axis like we normally have it being. Okay? And I have these sort of bowl shapes occurring above and below. They should look like they're the same size, and mine don't, but, you know, that's the way it's going to go today. And like you told me, it's a hyperboloid, sorry, of 2 sheets. All right, you ready for a list of homework? It's not as long as the list have been.
Is the whole homework to be sketching?
Some of it will. Some of it's going to be matching as well, where they're going to give you pictures and you're going to figure out which one it is. In fact, I'm pretty sure, if I remember right, the first 6 problems or whatever are matching problems. So it's 806, numbers 5 through 10. That's the part I think is matching. And then you have a few, 11, 12, 14, 16, 17, 20, 23, and 24. And you're going to be doing just like what we did, right? You're going to be drawing a sketch, identifying the correct axis, putting it in a standard form if you need to manipulate anything, those kinds of features.